Hello students, welcome back. This is the last lecture of your course. One of the students requested me to solve problem 18 from chapter 5. So in this video lecture I will solve problem 18, and you know that this is the last lecture, so you have to prepare for the final exam. And as I already mentioned that the final exam will be take-home exam, I will give you few problems, maybe around 5 problems on Tuesday 14th of July, and you have to solve those problems and you have to submit the solved problems on Wednesday before 12 p.m. So the statement of the problem is that a satellite travels around the Earth in a circular orbit of radius r. The angular speed of the satellite varies inversely with its distance from Earth according to omega square equals k over r cube, where k is constant. Observers in the satellite see an object moving nearby, also presumably in orbit about Earth. To describe its motion, they use a coordinate system fixed to satellite, with x-axis pointing away from Earth and y-axis pointing in the direction in which the satellite is moving. Show that the equations of motion for the nearby object with respect to the observer's frame of reference are given approximately by x double dot minus 2 omega y dot minus 3 omega square x equals 0. The second equation is that y double dot plus 2 omega x dot equals 0. So here you see I prepared one schematic. So this is the satellite. So as they mentioned in the problem, they use the coordinate system fixed to the satellite with x-axis pointing away from the Earth and y-axis pointing in the direction in which the satellite is moving. So satellite is moving in this direction here, and the distance of satellite from the Earth is r. So this is the object. It is also moving around Earth, and its distance from Earth is r naught, and its distance from the satellite, the distance of object from the satellite, is r. Suppose a naught is the acceleration of satellite and omega is its angular speed. And it is given that this angular speed, the scale of this angular speed, is equals k over r cube, and k is constant. The object is also moving around Earth in circular radius of r naught. So this is the object. So this object is also moving around Earth with radius r naught, and the angular speed of the object is omega naught. The angular speed of this object, it is omega naught, which equals omega k unit vector. The acceleration of object relative to Earth equals a naught, small a naught. Here we will use equation 5.2.14. It is in your book, and based on the given case, it is the most suitable equation to use. So in this equation, it gives the acceleration in the fixed axis. This equation, when if there is no a naught, you have to keep in your mind, if this term is not included, this a naught, if this term is not included in this equation, then this equation gives the acceleration in the fixed system in terms of position, velocity and acceleration in the rotating system. So in the given case, so by adding this term, this a naught term in this equation, we get the general equation for transferring from fixed system to the moving or rotating system. So in the given case, as the case is given in this problem, we have this equation. This is the a naught, as it mentioned the acceleration of the object relative to the earth, which equals a plus 2 omega cross r plus omega cross r plus a naught. So this is equation 1 for this problem. So as I mentioned, when we add this term a naught, so we get the general equation for transferring from fixed system to the moving and rotating system. So the term in this equation, in equation A, this term, it is Coriolis acceleration. It appears when the particle moves in a rotating coordinate system, because the object, it is moving in the rotating coordinate system. And this term omega cross r, it is centripetal acceleration. I believe you learned all these in your theoretical class. So this centripetal acceleration, it is the result of the particle being carried around a circular path in the rotating system. So by rearranging this equation 1, we will get a equals a naught minus 2 omega cross v minus omega cross r. So I named this equation as a. So here actually we will solve the three terms like a naught, this is acceleration, then a naught, capital A naught, and omega cross r. So we will actually simplify these terms, and I name these terms as x equals a naught minus capital A naught minus omega cross r. This term, it will be added later in x after simplification. So in my actually I cannot draw a proper circle. Yeah, this is much better than before. So yeah, so this is the equation 2. We will add the Coriolis acceleration later after simplifying x, as I mentioned in the previous slide. So there is an example 5.2.1, so you should check that. In that example, based on the conditions, acceleration equals omega naught cross r naught. So because this small a naught or capital A naught, both are the accelerations. One is for the object and one is for the satellite. So for satellite, a naught, capital A naught equals omega cross r, and from the figure we note that this small r equals r naught minus r, just addition and subtraction of vectors. So if we put these values in equation 2, we will get x cross omega naught cross r naught minus omega cross r minus omega cross r naught minus r. So we simply substituted these values in equation 2. So we know from the problem statement that omega naught square r cube equals omega square r cube, because k is constant there, and this angular frequency of the object equals the angular frequency of the satellite. So x equals omega naught square. This is just simplification of the previous equation. Omega naught square or naught minus omega square or minus omega square or naught plus omega square r. So these two terms, they are same but their signs are opposite, so we will simply cancel them. So this is the simplified result for x. And from this relation we can get the value of omega naught square, and we will put this omega naught square in this equation, so after putting the value we will get x equals omega square r naught r cube over r naught cube minus omega square into r naught. So again we will just take the common omega square, so x equals minus omega square r naught into 1 minus r cube over r naught cube. So this is equation 3. This is the actually value of x. Now we can add Coriolis acceleration in this x. So from the figure we know that r naught equals r plus small r. So to take the r naught square, like this r naught square, so the r naught square mean r naught dot r naught, so this equals the r naught, this term equals the r naught, and this term is also equals the r naught. So if we multiply both, so it is r naught square. So these equals, if we multiply them after simplification, we will get r square capital R square plus small r square plus 2 small r capital R cos theta. So for the case if the r is very small, then this r naught square equals r square into 1 plus 2 cos theta over r. We will just take 3 over 2 on both sides. For simplification we want to take actually r naught cube, because we will substitute in the previous equation, so we need r naught cube. So for that we actually took 3 by 2 here. So after simplification we got r naught cube equals r cube into 1 plus 2 cos theta over r whole power 3 by 2. So this term we need actually this term, so we have now, so putting this term in equation 3, this is the equation 3. So here we will put the value of this term. So x equals minus omega square r naught into 1 minus into 1 plus 2 cos theta over r whole power minus 3 by 2. Okay, so after simplification we got minus 3 by 2 here. So again for smaller r we have x approximately equal to 3 omega square r naught over r cos theta. So here because this is the equation A, and from equation A we got that A equals x minus 2 omega into v, 2 omega cross v, and we have the value of this x now. So we will simply put that value here in this equation. Yeah, but before that we will simplify 2 omega cross v. So here this is the simplified case, 2 omega k unit vector. It is given like this omega, it is given in the problem that omega r omega naught equals omega r omega k unit vector. And this v equals I x dot plus, because v component, v is the velocity and we have velocity components in x and y. So again we will just simplify, we will multiply this with first with I, with this one, and then with the same term we will multiply with j, and you know that k cross I equals minus j, this k cross I, it equals minus j, and this k cross j equals I unit vector. So here after simplification we have the results like this. Now equation 2 becomes based on that simplification. So this is actually the equation 2. So after that simplification we have A equals 3 omega square cos theta I unit vector plus 2 omega y dot I unit vector minus 2 omega x dot j unit vector. And we know that this acceleration, the one more thing, that because in the statements there is no cos theta, so simply we have to put this cos theta equals to x just to get the desired results. So the above equation, after substituting cos theta into x, cos theta equal x, A equals 3 omega square x I unit vector plus 2 omega y dot I unit vector minus 2 omega x dot j unit vector. This is equation 4. So we know that the acceleration, the components of acceleration equals x double dot, because it is acceleration. Velocity is x single dot and acceleration is x double dot. So x double dot iota unit vector plus y double dot j unit vector. So equation 4, now equation 4 becomes, the left hand side of the equation 4 we just replaced with these terms. Here you can see the right hand side of the equation is same. So comparing the coordinates, first we will go and compare the coordinates with respect to the I unit vector. Yeah, it's better to remove this and draw the smaller circle. I'm just practicing it. Yeah, so so when we compare, so x double dot, this I unit vector, here there are two I unit vectors, so this x double dot, it should be equals 3 omega square x plus 2 omega y, 3 omega square x here you see, and 2 omega y. So we have these terms now, and with simplification, so this is the equation of motion, x double dot minus 2 omega y dot minus 3 omega square x equals 0. And for y, if we compare this term, this term with this one, because it contains j unit vector, so uh, so this y, this term is negative, and here it should be negative, and y double dot minus, so it should be positive here, positive omega x, 2 omega x dot equals 0. I don't know where we did the mistake, but let me check again. Yeah, I checked the statement of the problem, so it is correct. Yeah, this is correct, because here this is the negative term and it should be negative here, and when we take it to the positive, to the left hand side, so this is the equation that is demanded in the statement of the problem. So y double dot plus 2 omega x dot equals 0. So this was the problem 5.18. we solved it, because you are lucky that these lectures are stored. Whenever you are confused, you can refer to these lectures. So this is the benefit of video lectures, but you have to do practice by yourself. And because when I asked you, when you face the problem, when you face the difficulty in solving problem, you should ask me. And I am surprised that in the class of more than 30 students, only 2 students requested me to solve the problems. So there are two things. One is that maybe all the students, they are doing practice and they are not facing any difficulty. The other reason is that maybe you are not watching the video lectures and you are not taking this serious. Anyhow, the video lectures are saved. You have to do practice and you should prepare yourself for final exam. Thank you.